Hello, welcome to lecture 25, which covers the topic of angular momentum. So far, we may have noticed a trend. The trend being, we are busy relating linear motion to angular motion. So far we have related a lot of equations, a lot of variables, a lot of quantities from linear motion and translated them or transformed them into or even defined new variables in angular motion using linear variables. In this chapter, we will talk about linear momentum. We know linear momentum from our study in chapter 7. And linear momentum, because there is a thing like linear momentum and it is governed by or determined by linear variables like v or velocity, it is logical to only have momentum that is related to rotation of an object, and we call that angular momentum. Okay, since p equals mv is the equation for linear momentum, similar to what we have done for forces and energy, we can relate this equation to writing down our own equation for angular momentum, which becomes p is replaced by the symbol of L, which denotes angular momentum, and that is equal to I times omega, because mass is replaced by moment of inertia for angular motion, and v is replaced by the angular speed, omega. The important thing to notice is that L is not a vector in the complete sense of the word as P was. Okay, L is what we call a pseudo vector. Why is it a pseudo vector? It is because it is not really a vector. It is not a vector in the sense of very simply or naively we cannot simply denote its direction by a positive or negative sign like we used to do for momentum or any other regular vector. L and torque and all of those angular variables like omega and alpha, their direction are more or less like related to clockwise or counterclockwise rotational motion. Okay, so that is a very naive definition of what a pseudo vector is, but we don't need to get much into the specifics of it. So moving on, we knew that there was a conservation law for momentum in collisions. The initial momentum was equal to the final momentum whenever there was no net external force acting on the system. Likewise, we have a conservation law for angular momentum as well, whenever there is no net external torque acting on the system. And so we can only understand this stuff better if we jump right into examples. Let's do that. Okay, so in this example we have a figure skater. She's spinning. Pardon me for my very bad drawing, but it'll have to work. So when she spins, we can treat this situation like a collision, because once before she was spinning with her arms extended outside, and then her arms are close to her body, so she changes stance while spinning. So basically we can treat the arms colliding with the body and treat this as a collision problem. Okay, alright, so what is given to us? It is said that a figure skater spins with her arms extended with a speed of 5 radians per second. So this is the speed of how fast she is spinning, and by the units radians per second, we can say that we can actually note that this is angular speed. When her arms are extended, our moment of inertia is given to us to be 2.35 kilogram meter squared. Alright, but then she changes her stance so that her arms are now close to her body, and she has now decreased her moment of inertia to 0.36 kilograms meter squared. So how you might ask, is her moment of inertia changing when she's bringing her arms close to her body? Well, We remember that very basically moment of inertia depends on the mass and how the mass is distributed. Okay, is the mass close to the center of mass, or how the mass is distributed over the system we are considering. She is basically, by moving her arms back and forth from an extended position to a closed position, she's changing her distribution of mass, and so decreasing her, so changing her moment of inertia. Why does it decrease though? Well, moment of inertia is also dependent on the distance away from your axis of rotation. So if you think about her axis to be her skeleton, then if she's close, if her hands are close to her own skeleton, then obviously the distance from the fixed axis of rotation, that is her skeleton, has decreased, and so her moment of inertia has also decreased. Okay, just a reasoning why the moment of inertia should decrease. All right. Now it is asked that how fast does she spin in this position when her arms are close to her body. Okay, so as we have said, we can consider this as a very straightforward collision problem. Let's attempt our first solution using collisions. But now this is not a simple linear collision. This is a rotational collision because she's spinning. For a rotational collision means that there is no external torque. Okay, so torque net is 0. The net external torque is 0. Alright, no other force is making her rotate rather than herself spinning around her own axis. Therefore, net torque is 0. If that is the case, we know that there is angular momentum conservation. So Li equal to Lf. What is Li? Li is I initial minus times omega initial. Lf is I final times omega final. I initial was our moment of inertia with arms extended, which is 2.35. Omega initial was 5 radians per second. I final is 0.36, and omega final is what we are looking for. So if we divide both sides by 0.36, we get our spin speed with her arms close to her body to be 32.6 radians per second. Alright, this is a very easy method to find speed whenever we have an angular sort of collision. Alright, just by using conservation of angular momentum. Let's look at another example. Okay, in this second example, we have a merry-go-round which has a mass of 200 kilograms with radius of 1.5 meters, and it spins in a counterclockwise direction with a speed of 6 radians per second. A 50-kilogram child decides to jump straight towards the center of the merry-go-round, but she lands 0.1 meters from the edge. Okay, assuming that they started on the ground, the child started on the ground, then what is the speed of the merry-go-round after the child lands on it? Alright, again we have an angular problem, of course, because we are talking about angular momentum. How foolish of me. But it is again sort of a collision because two bodies are coming together, right? The child is coming in contact with the merry-go-round. Before they were separated, but now they are bound together, joined together after the child lands on it. Alright, so since there is a collision and there are no external forces on this system of the merry-go-round and the child, we can again say that there is no net external torque. Right? This again means that the angular momentum is conserved. So what is the angular momentum initial? Well, the angular momentum initial will have the initial of the merry-go-round, initial angular momentum of the merry-go-round. Initial meaning that child is on the ground, child on ground, and final position means child is on the merry-go-round. Alright, so initially we will have the moment of inertia of the merry-go-round plus the moment of inertia of the child, if there is any, and finally we will have the moment of inertia of the merry-go-round and the child. Alright, because there are two objects in the system, so we'll have the summation of two moment of inertia. Alright, initially the kid was at rest, right? So if the kid is at rest, obviously angular speed is 0, so they had no angular momentum as well. So only momentum that we need, or only angular momentum that we need, is initial for the merry-go-round and final for the merry-go-round and the child. Initially, the merry-go-round was moving or rotating, more precisely, at some speed, so it has some angular momentum. Angular momentum is defined as I omega. Therefore, I of merry-go-round times omega initial before the child gets on it, equal to, for the final case, we have I merry-go-round times omega final plus I, let's call it kid, times omega final. Now why have I denoted both of these omegas to be the same? Because now the kid is part of the merry-go-round, so they're rotating together, therefore the rotational speed after they're together must be the same. Alright, so we can simplify it a little bit more. Merry-go-round times omega I equal to, we can take out omega f and write just I mgr plus I kid times omega final, and our target is omega final. Alright, now what is the moment of inertia for merry-go-round? Well, merry-go-round is looking like a solid disk, so we can basically use the inertia for the moment of inertia for the solid disk, which is from the table collected to be as 1/2 m r squared. R is the distance from the fixed axis of rotation, and from the table you get it from the center of mass, and so the distance from the center of mass to the edge of the merry-go-round is what is rotating, so that is just the radius of the merry-go-round. Alright, so that is the moment of inertia for the merry-go-round. What is the moment of inertia for the kid? We can model the kid as a point-like object. Okay, so we know that for a point-like object, the moment of inertia is simply the mass times the distance from the fixed axis squared. Alright, we have to determine what this, let's call this R1, the radius of the merry-go-round, and let's call this R2, the distance from the axis of rotation to the center of mass of the child. R1 is just the radius of the merry-go-round, alright, because fixed axis of rotation is at the center of the merry-go-round, and any particle or any object that is at the edge of this merry-go-round is what we consider to be farthest away, causing the rotation. Alright, R2, what is R2? Well, remember that the child length, actually this is 0.1 meter. The child length 0.1 meters from the edge of the merry-go-round. So this distance right here is 0.1. Okay, and we know that from the center to the edge of the merry-go-round, the radius is fixed to be 1.5. So if this small distance is 0.1 meters, where the child lands, then how far is the child from the center or the fixed axis of rotation? It is just 1.4. So R2 is 1.4 meters. Now we have everything to solve for omega f. Let's go ahead and do that. Therefore, this equation becomes, replace IMGR with the one for the disk, 1/2 mass is 200 for the merry-go-round times R1 is 1.5 squared times omega I. Omega I is the speed, angular speed before the child gets on it, so 6 squared. This is equal to 1/2 200 times sorry, there is no square here. This on the right hand side we have 1/2 times 200 times omega squared, which is omega final squared, which we don't have till now. That's our target. And this is sorry, I missed something. We have 1/2 times 200 the mass of the merry-go-round times the R1 again, 1.5. That gives me the moment of inertia for merry-go-round plus I kid. Kid is modeled as a point-like particle or point-like object. So we have the mass of the kid, which is 50 kilograms, times the distance away from the fixed axis of rotation of the merry-go-round, which is R2, which is 1.4 squared, times omega final. Alright, so whatever this comes out to be, and let's see if I have calculated what this is. Whatever this comes out to be, and it turns out comes out to be 225 plus 98, and this comes out to be 225 times 6. Okay, and if you divide both sides by 225 plus 98, and remember there is a omega final multiplied on this side, then we get the final speed of rotation after the child gets on the merry-go-round, and it comes out to be 4.18 radians per second. Alright, so these are some ways we can use angular momentum and conservation of angular momentum to solve problems like these. Alright, I hope this makes some sense, and thank you for listening and watching this video.